Hello everyone, welcome back to the CSE Guy. Today we are diving into the fascinating world of reinforcement learning. We will explore its key elements, Markov decision processes, dynamic programming concepts, and various algorithms like value iteration, policy iteration, Q-learning, and more. So let's get started. First, let's explain the elements of reinforcement learning, focusing on the roles of the agent, environment, and reward. First, agent. The agent is the learner or decision maker that interacts with the environment. It takes actions based on its current state and learns from the feedback it receives. For example, in a game of chess, the player is the agent making moves. Second, environment. The environment is everything that the agent interacts with. It provides the context in which the agent operates and responds to the agent's actions. In our chess example, the chessboard and the opponent are part of the environment. Third, reward. The reward is the feedback signal received by the agent after taking an action in a particular state. It quantifies the success of the action in achieving the agent's goal. For instance, in chess, capturing an opponent's piece might yield a positive reward, while losing a piece could result in a negative reward. Example, consider a robot learning to navigate a maze. The robot agent moves through the maze environment and receives rewards for reaching the exit or penalties for hitting the walls. The agent learns to maximize its total reward by adjusting its actions based on the feedback it receives. Next, let's describe Markov decision processes or MDPs in detail. A MDP is a mathematical framework used to model decision making in situations where outcomes are partly random and partly under the control of the agent. MDPs consist of four key components. First, states. S. This represent all possible situations the agent can be in. For example, in a grid world, each cell can be a state. Second, actions. A. There are the choices available to the agent in each state. For instance, in a grid world, the actions might be move up, move down, move left, or move right. Third, rewards are. This is the feedback received after taking an action in a state. It can be a scalar value that indicates the immediate benefit of that action. Fourth, policies. A policy is a strategy that the agent employs to determine its actions based on the current state. It can be deterministic or stochastic. Importance of the Markov property. The Markov property states that the future state depends only on the current state and action, not on the sequence of events that preceded it. The property simplifies the modeling of decision-making processes, allowing us to use MDPs effectively in reinforcement learning. Now let's describe the difference between policy evaluation and policy improvement in dynamic programming. Policy evaluation is the process of calculating the value function for a given policy. It estimates how good a policy is by determining the expected return, cumulative reward, when following that policy from each state. This is done iteratively until the value function converges. Policy improvement, on the other hand, involves updating the policy based on the value function obtained from the evaluation step. The goal is to find a better policy that maximizes the expected return. This is typically done by choosing actions that lead to states with higher value. Contribution to solving an MDP. The combination of policy evaluation and improvement leads to an iterative process known as policy iteration. By repeatedly evaluating and improving the policy, we can converge to the optimal policy that maximizes the expected return for the agent. Next, let's explain the value iteration algorithm, including its steps and how it converges to the optimal value function. Value iteration is a dynamic programming algorithm used to compute the optimal value function for an MDP. Here is how it works. First, initialization. Start with an arbitrary value function for all states, often initialized to 0. Second, update step. For each state, update the value function using the Bellman equation. Third, convergence check. Repeat the update step until the value function converges, meaning the changes in value are below a certain threshold. Convergence to optimal value function. Value iteration converges to the optimal value function because it systematically updates the value estimates based on the expected returns of all possible actions, ensuring that the values reflect the best possible outcomes over time. Now let's describe the policy iteration algorithm, explaining how it alternates between policy evaluation and improvement to find the optimal policy. Policy iteration consists of two main steps that are repeated until convergence. First, policy evaluation. For a given policy, calculate the value function using the Bellman equation until it converges. This step estimates how good the current policy is. Second, policy improvement. Update the policy by choosing actions that maximize the expected return based on the current value function. This is done by selecting the action that leads to the highest value for each state. Process. The algorithm alternates between these two steps. After each policy improvement, the new policy is evaluated and the process continues until the policy no longer changes, indicating that the optimal policy has been found. In summary, policy iteration is an effective method for solving MDPs as it guarantees convergence to the optimal policy through systematic evaluation and improvement. Next, let's discuss temporal difference learning and compare temporal difference prediction TD of 0 with temporal difference control TD of 2. Temporal difference learning is a reinforcement learning approach that combines ideas from Monte Carlo methods and dynamic programming. It allows agents to learn directly from raw experience without a model of the environment. First, TD prediction. TD of 0. This method updates the value function based on the current estimate and the immediate reward received after taking an action. The update rule is the learning rate. The update rule is Vs of 0 and alpha minus Vs, where alpha is the learning rate, R is the reward, and S dash is the next state. Second, TD control, TD of 2. This method extends TD of 0 by considering multiple future rewards, allowing for more accurate value estimates. It uses a more complex update rule that incorporates the expected returns over multiple time steps. So let's compare them. While TD of 0 focuses on immediate rewards, TD of 2 takes into account future rewards, leading to potentially faster convergence and better performance in certain environments. Now let's provide a detailed explanation of Q learning, including its algorithmic steps and how it achieves off-policy control. Q learning is a model-free reinforcement learning algorithm used to learn the value of actions in states, known as the Q values. The goal is to find the optimal action selection policy. So what are the algorithm steps? First, initialization. Initialize the Q values for all state action pairs arbitrarily, often to 0. Second, action selection. For each episode, select an action using an exploration strategy such as E-greedy, which balances exploration and exploitation. Third, update rule. After taking an action and observing the reward and next state, update the Q value. Fourth, repeat. Continue this process for a number of episodes until the Q values converge. Off-policy control. Q learning is considered off-policy because it learns the value of the optimal policy independently of the agent's actions. This allows it to learn from experiences generated by different policies, making it versatile in various environments. Finally, let's discuss the concept of off-policy learning in reinforcement learning, focusing on how QL learning differs from on-policy methods like SARSA. Off-policy learning. In off-policy learning, the agent learns about one policy while following another. This means that the learning process can utilize experiences generated by a different policy, allowing for greater flexibility and efficiency in learning. Second, Q learning. Q learning is a prime example of off-policy learning. It learns the optimal action value function regardless of the policy being followed. This means that even if the agent explores the environment using a suboptimal policy like epsilon not greedy, it can still learn the optimal policy by updating its Q values based on the best possible actions. On policy learning. In contrast, on-policy methods such as SARSA, state action, reward state action, learn the value of the policy being followed. SARSA updates its Q values based on the action actually taken by the agent, which means it learns the value of the current policy, including the exploration strategy. So what are the key differences? First, learning process. Q learning updates its Q values based on the maximum future reward, while SARSA updates based on the action taken by the current policy. Second, exploration versus exploitation. Q learning can learn from experiences generated by any policy, while SARSA is constrained to learn from the policy it is currently following. In summary, off-policy learning, as exemplified by Q-learning, allows for more robust learning strategies by leveraging experiences from various policies, while on-policy methods like SARSA focus on learning the value of the specific policy being executed. So that's it for today. Thank you for joining me today. Don't forget to like, subscribe, and hit the notification bell for more content. See you next time. Thank you.